Serão os professores André Costa Silva, da UF, coordenador técnico da ABM também, e o professor Fernando Cosme Riso Assunção. O professor Riso também é o editor pela ABM da revista TMM, TMS, junto com o Universidade de São Carlos, ex-presidente da ABM, e na gestão do professor Riso foi introduzido a área de materiais. A ABM era a Associação Brasileira de Metais e passou a ser a Associação Brasileira de Metalurgia e Materiais. Mais tarde, alguns anos depois, nós introduzimos também a área de mineração. Então, hoje a ABM é a Associação Brasileira de Metalurgia, Materiais e Mineração. Tem gente que pergunta, por que mineração não vem primeiro? Não, porque ela foi criada por último, não é? Então, a logomarca hoje da ABM, a nova logomarca, já tem um Mzinho que é em vermelho, justamente, na hora que você vira um pouquinho, parece um 3, que são as 3 áreas de conhecimento que a gente atende aqui. Só para contar um pouquinho de história para vocês. Né? Aqui o diretor, o professor Riso, é professor da PUC do Rio de Janeiro, é diretor do CGE, Centro de Gestão e Estudos Estratégicos, lá em Brasília, né? Além do professor André Mark Meias, que é o editor-chefe da nossa revista, da Universidade da Califórnia e editor-chefe da nossa revista. Professor Rich, ficamos muito honrados com a sua presença e eu agradeço você ter aceitado o convite e para nós é uma honra muito grande. A associação, esse ano, conta aqui, você já deve ouvir algumas aberturas aqui, nós estamos com mais de 3.000 pessoas aqui hoje no nosso evento, é um dos recordes nossos, com 96 estandes. Então, esse ruído que está vindo lá de fora é porque nós estamos com muita gente e está adaptando aqui o espaço. Eu agradeço a vocês todos. O professor Sérgio Neves falou assim, ali está a turma do IME, não é? A turma do IME. Sejam bem-vindos aí à turma do IME aqui, do professor Sérgio Neves, que é fera aqui também. Então, agradeço a vocês todos e passo a palavra aqui, retorno aqui para o André. Obrigado, André.
Obrigado, Leão. Esse momento da entrega do Lifetime Achievement é muito importante, e é uma sessão especial. Não sei se vocês se lembram, mas o primeiro vencedor foi o professor Dirk Habe, que recebeu aqui, que também dispensa apresentações, né? E é um prêmio que tem sido notável pela qualidade dos laureados, principalmente, né? No ano passado, nós tivemos um professor da China que deu uma aula que nos deixou aqui boquiabertos também, né? Que eu tenho certeza que vai se repetir com a aula do professor Rich. Eu estava olhando aqui o slide do professor Richard e é praticamente assim, quando você olha os coautores e os colaboradores, é praticamente um who is who na área de metalurgia, né? Quer dizer, você tem desde o Mark Asta de primeiros princípios, professor Apelian, que é do meu tempo, o professor Maias, que dispensa apresentação, Lavernia, quer dizer, são nomes que dá para ter uma ideia, assim, né, dos coautores do professor Richard. Você imagina o trabalho dele, né? Professor Richard, eu imagino que vocês todos conheçam o trabalho e a trajetória dele, mas, assim, só para ter uma ideia, humbling, né? Ele tem mais de 950 publicações, tem um H de 150, né, para quem trabalha no mundo acadêmico, né? Quer dizer, isso quer dizer que o 150º paper dele é citado mais de 150 vezes. Então, né, eu acho que o meu paper mais citado é 180 vezes, o meu número 1. Né? Então, só para você ter uma ideia, quer dizer, se você botar o ranking das publicações dele por número de citações, quando chega em 150, esta publicação tem 150 citações. Né? Então, quer dizer, assim, é bacana porque a gente tem a oportunidade de ver os gigantes que estão abrindo caminho para a gente progredir na ciência, né? Quer dizer, para vocês principalmente, nós estamos no acaso, né, das nossas vidas científicas, mas vocês vão ter que trabalhar para chegar perto do que o professor Rich fez e tem feito, né? Ele é membro, obviamente, da National Engineering, da Sociedade de Engenharia dos Estados Unidos. Ele é do Laboratório Nacional Lawrence Berkeley. Ele também é da Royal Society, membro honorário, né? Quem se lembrar que as pessoas assim como Newton, Hooke e outros foram membros da Royal Society, tem uma certa ideia do que significa, né, ser admitido na Royal Society. Ele foi consultor, e assim que a gente fizer aqui, eu vou terminar gastando todo o tempo, né, Mark, falando do currículo do professor Rich, e nós não vamos ouvir o professor Rich. Então, ele foi consultor de diversas empresas grandes. Ele tem uma carreira que cobre uma variedade de assuntos extrema, né? Está atualmente trabalhando uma das áreas, são essas ligas de alta entropia, ou ligas de multicomponentes principais. E eu acho que eu não vou passar muito mais tempo apresentando o professor, e vou, então, convidar, please, Professor Rich, would you kindly take the stage and give us your talk?
Thank you very much for the introduction, and thank you very much for inviting me here. I really appreciate the chance to come back to Brazil. I was here 40 years ago, so it's really a great honor to come back. I'm going to talk about high entropy alloys. I'm fully aware that steels are probably the most important metallic alloy that we have, but these materials are very interesting, and they may have a future because of their properties, which are really quite extreme. They may be a little too expensive for many materials people, but I think in things like aerospace and maybe space exploration, their costs will not be so important, and they do have very interesting properties. This work, I have a number of people who've helped me with this. Mark Astor and Andy Miner are both part of my program. David Cook is my private... Sorry?
Quem precisar de fone para tradução simultânea, tem ele fora, por favor, tá?
Okay. David Cook is one of my prime students, and you'll notice some other names there of importance. Mark Myers, for example, interacted us with his expertise on high-impact behavior. I'll talk a little bit about that. So, let me just use this here. Okay, so I want to talk about two types of high-entropy alloys. There are two classes. They've been around now for about 20 years. They've become important in the last 10 years, and they've done an awful lot in terms of monopolizing the published work on metallic alloys. It's given a new birth almost to mechanical properties, which has slipped down the list of important aspects of material science to things like batteries and perovskites and graphene. But these are really engineering alloys with engineering applications. I'm going to talk about the so-called face-centered cubic alloys. These are mainly based on the chrome, cobalt, nickel alloys. There are a number of them, and I'll explain a little bit about several of these materials. They're renowned for their very, very high toughness and ductility. They are, they're perfect in terms of properties that we need in structural applications. The second part, I'm going to talk about the body-centered cubic alloys. These are sometimes called refractory high-entropy alloys, and these have very, very high strength that can exist at very high temperatures. They are potential replacements for superalloys, for example, although I don't think that's going to happen very soon. And I'll look at a number of these materials over a range of temperatures. They don't have the toughness that the FCC materials do, but they have other properties. So these are interesting applications, but they're quite different. So let's look at the FCC first. These were the ones that were first invented. They're sometimes called the Cantor alloys. They're chrome, cobalt, nickel. Sometimes they have manganese and iron in them. People never studied these multiple principal element alloys. Most of our alloys are single element with a number of other materials added. You know, steels, iron dominated. Superalloys are nickel dominated. But these have almost equiatomic, in many cases, applications of elements with very, very different crystal structures, but they end up with a single phase material, in many cases, not all, but these alloys did. And one of the big applications for these, if you look on the left-hand side here, you can see stress-strain curves, uniaxial stress-strain curves. The bluer color means cooler. This would be liquid nitrogen. This would be in room temperature. And you can see these alloys get stronger as you go to lower temperatures. Well, that's no surprise. But the thing that's interesting is they get more ductile. The ductility of this alloy at liquid nitrogen temperatures is 90%. The ductility at room temperature is about 70%. So they have really interesting properties. And what interests me, I'm a fracture mechanics person, I was interested in their toughness. And these are R curves, resistance curves. They're the J integral, which is a non-linear elastic parameter, plotted against the crack extension. And these, again, the room temperature has high toughness, but the very low temperature has really high toughness. And these alloys have toughnesses that are above 300 megapascal root meters. Now, these are enormous numbers. Most steels don't get much above 100 megapascal root meters. Silicon is 1 megapascal root meter. These are up around 300 at liquid nitrogen temperatures. So they are fascinating alloys. They have remarkable fracture resistance. And if we look at them, they have a number of different mechanisms. This is the structure here of the, well, you're not seeing my thing here. That's interesting. This is the structure on the left-hand side, right-hand side here of the alloy. It's a lot of twinning. It's a twin microstructure. And what we find happens is that they have extreme strain hardening. You can see how the hardening becomes greater at lower temperatures. And the reason for that is a sequence of mechanisms. It's an unusual sequence of mechanisms, but it involves dislocation motion. It involves the formation of stacking faults, which would be the dissociation of dislocations. It involves twinning, and it involves the formation of another phase, a phase transformation. And at higher strain rates, as Mark showed, you can see it becomes amorphous as well. So there's a series of mechanisms of plastic deformation which prolong strain hardening. That's good because the material's harder. It's good because it delays necking, so it increases ductility, and you've got the perfect sort of recipe for high toughness materials. We can see some of these mechanisms here. On the left-hand side here, I'm showing dislocations coming onto a twin band, and you can see how the dislocations are stopped by the twin band. That's perfectly normal. That's a hardening mechanism. But if we look at these same boundaries, these twin bands, they also provide a means for dislocations to move along those boundaries. They're like highways. So this is a hardening mechanism by the process of the twin band. This is actually a ductility mechanism on the formation of the twin bands. So again, we've got this combination of strength and ductility, which is often works the opposite way around, high strength, low ductility. But here, they work together because of this sequence of mechanisms. And this one in the middle here is what we see at very, very low temperatures. This is at nearly liquid nitrogen temperatures in the transmission electron microscope, you see these same pile-ups along a slip band, but there's massive cross-slip that occurs off those twin bands. So we've got the slip band, which is a hardening mechanism as the desiccations move, but we can see massive cross-slip as well, which is a ductility mechanism. So this is a really magical property where we can get strength and ductility leading to prolonged strain hardening and this really high toughness material. So we've taken these alloys down to liquid helium temperatures. We're down at about 20 Kelvin. We don't get down to 4 Kelvin because there's too much mass of the alloy. And we've looked, this is the original 5-component system. This is the chrome, cobalt, nickel. Again, room temperature, liquid nitrogen here, and we're going up to liquid helium here. And we get toughnesses now that are of the order of 460 megapascal root meters. The so-called crack growth toughness is above 500 megapascal root meters. This is the toughest material on record. So this, I mean, maybe these alloys are too expensive to make standard applications that we live with steels, but these are the toughest materials that have ever existed as far as we can see. And again, it's that sequence of strain hardening that gives these mechanisms. These are TEM studies, very planar slip, very planar formation of deformation. We see, of course, twinning, very, very fine twins, and we see the formation of another phase, which is it forms a hexagonal martensitic phase. That phase transformation absorbs energy, that further increases the toughness. So this is a really, really tough material because of this prolonged strain hardening by a sequence of deformation mechanisms. We've looked at some other aspects here, and this is basically working with Mark Myers. We looked at very high strain rate conditions. Now, if it's good at cryogenic temperatures, it should be good at high strain rates. And this is work done with Shiteng Zhao, who I think you know here. This was using Hopkinson bar, and we looked at this particular high entropy alloy, and we don't measure toughness here, but the absorbed strain energy is far higher than any other material that we've looked at before. So this is, again, a feature of these materials. They have very, very high strain rate fracture resistance. And again, we see these sequence of mechanisms of deformation by dislocations, dissociation, formation of another phase, the martensitic phase, and we see amorphous material. We went to even higher strain rates. This was done with laser shock. Again, this was Shiteng Zhao's work. And again, you can see all these mechanisms I've talked about, the very, very planar slip type material. We get twinning formation, and we get the formation of another phase. And there is amorphous regions here as well. I'm not sure what the amorphous regions do in terms of toughening, but they're another mechanism to give us this sequence of deformation. So these are really, really tough materials. They get tougher at lower temperatures, and they get tougher at higher strain rates, which is very intriguing. We've looked at some other applications of these to try and make them better. This was using a material where we could get more of the transformation. It's called a dual phase material. It has some martensitic material within it's an austenite phase, FCC, and it has a bit of martensite in the middle. So that promotes the TRIP, the transformation and use plasticity. And it's similar. It's simply a chrome, cobalt, nickel material. And you can see the one that has the transformation has much higher strain hardening and much higher strength. So we thought this will be even tougher. This will be a really tough material. The mechanisms are very interesting. It forms these stacking fault sort of structures. They're like tetrahedral stacking faults. And you can see these cross-ply imaging here. That's where the transformation takes place. It forms near the stacking fault because of similar hexagonal close-packed structure. And these stacking faults are extremely, let me go back again. They're extremely good at blocking dislocations. You can see a dislocation pile up here coming against the stacking fault, and it's very, very effective. So this seems to accentuate everything we've seen before. High strength, high ductility because of the motion of dislocations. But if we look at the properties, they're very interesting. These are toughness curves, toughness versus, that's crack extension. Red is room temperature, this is lower temperatures, and this, of course, is the temperature at liquid nitrogen. This was the original counteralloy. That's the one I've been talking about, or at least a version of that. It gets tougher at lower temperatures. But when I start to use too much transformation toughening, you can see we still get good toughness, but we don't see the very high toughness at lower temperatures. So too much of transformation-induced plasticity is a bad thing. And the reason is that the phase that it forms, the transformation absorbs energy, that's good, but the phase that it forms is a brittle phase. It's martensite. So you don't want too much of this, and in some of these dual phase or these trip-based alloys, they have too much of that phase and they don't get the super high toughness associated with lower temperatures. So it's an interesting sidekick. I won't talk too much about this, but we've also looked at additive manufactured versions of these materials. Additive manufacturing is very interesting. It can cause real problems in generating defects and voids, but you can generate structures that you can't generate any other way. And these are still basically nominally single-phase structures, but by using laser powder bed fusion, we can generate this sort of hexagonal type structure which has a B2 phase, which is like the coherent phase in a nickel-based superalloy, in a honeycomb type structure. So basically, these boundaries are very heavy in dislocations. So they act as barriers, but the material, because they're dislocations so much, the system is much more ductile. So we get quite high toughness with these materials. They have a lot of higher strength. This is a stress-strain curve, but this is the toughness curve, and you can see we start to still see higher toughness at lower temperatures. So these are interesting applications. They're a little different because we have these honeycomb structures with high dislocation densities. They're just a variant what I talked about before, but they do operate in a slightly different way because of additive manufacturing. This is one of these banana curves of toughness versus, I think that's ductility or yield strength. And you can see we get properties that are a little bit better up here with that technique. So that's mainly the story of the FCC. High toughness, high strength, high ductility, prolonged strain hardening by a sequence of these deformation mechanisms, which are very effective. And you can play with those. You've got lots of things to adjust when you're using an alloy with lots of elements in. The FCC are quite a different story. These are the so-called refractory alloys, and America is really excited about these because they can have applications for hypersonics, they can have applications for extremely high temperatures. Some of these alloys still have reasonable strength at 1600 degrees centigrade, so they're very interesting materials, but like most refractory alloys, they're brittle, so they don't have the toughness. So can we do anything about that? And they also have, they're kind of a little bit susceptible to environmental effects. So there's a huge potential with these materials, but there's lots of things to solve here. So these have, I think, become the principal elements that principal materials we've been looking at. And we've decided that maybe you can control these things by affecting the composition. You've got 5 elements or 4 elements. What can you do to get some ductility in these very, very high strength materials? This is a picture from Dan Miracle, which looks at the strength here as a function of temperature, I mean, most of our alloys drop down around 1200. This is nickel-based superalloys, but you can see these materials, these are these refractory high-entropy alloys, have strengths of several hundred MPa at temperatures as high as 1600 or higher degrees centigrade. So they really have a lot of applications. So I'm going to look at these. I'm going to look at three of them. One is called a refractory superalloy because it's like the superalloy in its microstructure. This one is a very famous one, niobium, moly, tantalum, tungsten. I think that's that purple one there, known for its very, very high strength. And I'm going to look at one of ours, which involves niobium, tantalum, titanium, and hafnium, which is a very different alloy. Now, these two are the ones that people have looked at first. Let's look at the so-called refractory high entropy, refractory superalloy. This is the superalloy because it has an ordered, basically, precipitate, a B2 precipitate. That's that dark phase, and you can see it there in a disordered matrix. So it's just like a superalloy, a nickel-based superalloy, and you can see the B2 phase is sort of cubic or cuboid in shape. There's a number of these alloys that are around. So we looked at this. You can see precipitate-free zones around the grain boundaries as well. So they look interesting. That's why they call them superalloys. But we don't think they're super at all. Most of the properties that have been measured on these refractory high-entropy alloys are measured in compression. And compression is not a good source for many of the fracture properties. This is this superalloy in compression. Beautiful, fantastic ductility. Look at the strength here, up around 3 gigapascals, high ductility. But if you measure them in tension, you get a very, very different story. This is the data in tension. Sorry. That's the data in tension. The strength drops from 3 gigapascals to 0.2 gigapascals, and the ductilities are all very, very small because they're brittle materials, and this is classic. So I think a false impression has been given to the community by a lot of people by doing everything in compression. We do toughness. Not many people look at toughness for some silly reason in these materials, and this is the toughness data, and as you can imagine, the toughness is terrible. This is this same superalloy. The toughness is below 10, and most of the time is below 5. Now compare that with the face-centered cubic structures that have toughnesses of 500 megapascals. Here we're down really, really brittle materials. And of course, if you look at the fracture surfaces, you get a brittle fracture. This is intergranular fracture, and this is not unusual for these materials. Why intergranular? Well, we looked at these materials, and what happens is the boundaries are set places where you get oxidation and the formation of a phase. In this material, it forms an aluminum zirconium precipitates, which cause the intergranular fracture, and it can lead to hydrogen embrittlement problems as well. So I don't think they should be called high-entropy superalloys because they're not very super if you test them in tension. But this is not a particularly unusual story. This is that famous niobium, moly, tantalum, tungsten material with incredibly high strength measured in compression. This is the stress-strain curves in compression, very, very high strength. We're up to 1200 here. Pretty good ductility, but it's all compression. But once you get into tension, very different story. There are the tension properties. The tension properties are all down in this little bit here, and you can see they break before you even reach the yield stress, and the ductility is very, very small. So this is the problem with these refractory high-entropy alloys. Fantastic in compression, fantastic strength, very high temperatures, but any tensile properties, and they're brittle as hell. They have very high ductile brittle transitions. And in fact, this is the toughness data, and again, you're dealing, depending on what you're looking at, you're dealing with toughnesses well below 12 megapascal root meters, which is worse than the most brittle steel you can get. The most brittle steel is about 20. This is way below that, half of that. So these alloys, I think, people are looking at them, but they need a lot of things done to them to make them more ductile. Their ductile brittle transition is too high. So what we've done, again, by the way, just quickly, you get oxidation in the boundaries, you form niobium oxides. This is why the grain boundaries are so brittle. So they have a high ductile brittle transition associated with boundary situations and probably with environmental effects in those boundaries. So we've tried something different. We have taken that alloy, and this one here, which is a combination of group 5 and group 6 elements, and we've put in group 4 elements, which are the titanium and hafnium. These are group 4. And we've generated an alloy which is, we think, quite remarkable. This is what the structure looks like. And it's, you can, by the way, you can roll it at room temperature. One of the things you have to do with these alloys, you have to break down the cast structure. If you're dealing with some of these refractory alloys, you have to roll them at some ridiculous temperature, like 1800 degrees centigrade, which is a big problem. But this one you can roll at room temperature. And look at the properties. Very, very different to what I've showed you so far. This is the stress-strain curves. And you can see here, we're getting strengths, very high strengths, not as high as the other ones, but pretty high strengths at liquid nitrogen temperatures, and we can go up to 1200, and we still get 200 megapascal root meter. So these do have reasonable properties. They could be stronger, we'll talk about that. But the thing that's amazing is their toughness. The toughness of the alloys I showed you before was all less than 10. This one is very, very high. The toughness is very, they stay above about 50 in all conditions. They're about 200 or so at room temperature, but they have toughnesses of close to 100 megapascals at liquid nitrogen temperatures. This is a BCC material. It should have a ductile brittle transition. The toughness should have dropped to 0, but this is very, very high. And so it's a very interesting material. There's the banana curve again, and we have this alloy is way up here, which is not what we surprised. It's high strength because it's a BCC material, but not as high as some, of course, but it has high ductility. And this is in tension, not in compression. Why? Well, one of the intriguing things about this alloy is it has a sequence of deformation mechanisms. By the way, it doesn't form strain hardening. The FCC material strain hardened. These alloys have no strain hardening at all, which is intriguing. But if you look at the mechanisms, this is at very low temperatures as we increase temperature. At the low temperatures, we get a lot of, we get some twinning, of course. Twinning is throughout. We get regular dislocation activity. I'll show you we get some transformation. But the kicker is we form these kink bands. These are these very thick bands coming out. Now, kink bands are unusual. They were first mentioned by Orwan in the 1950s. Very little work has been done on kink bands. And these, we think, are the reasons these alloys are so tough. Kink bands promote instability, necking, but they don't here. They promote deformation and move it away from the cracked tip. And of course, at very high temperatures, then the materials basically recrystallize. So there's work to be done to push the temperature a little higher. There's no question about that. But this is the kink band formation. And the kink bands look like this. They are basically where the material forms a kink. It basically moves to maximize the critical resolve shear stress. Interesting. And it's associated with multiple dislocation sources. In this case, we get 2 sets of dislocation motions. These are the 111, 110s and the 111, 112s. And they form in the boundaries. And they're so close together in the boundaries, you can't even see them separately. But that's the key for these mechanisms, that they form this additional deformation mechanism. And you can see them very clearly here. These beautiful kink bands that come out. They're formed at all temperatures. They're not so strong at lower temperatures. They're probably stronger at higher temperatures. But they're a very, very interesting mechanism. But we also get dislocation activity. People think in BCC structures, screw dislocations are key because they're the ones that have more difficulty to move. But in these alloys, we see we've done G.B analysis, and the different colors tell us whether they are screw or edged or mixed dislocations. So we get a lot of dislocation activity and a lot of slip mechanisms. That's associated with the group 4 elements, and that generates this kink band formation. So we've even gone to liquid helium temperatures in these materials, and this is we're still trying to fight over this, but we still get pretty good ductility and very high strength at liquid helium temperatures, which is intriguing. We get an intergranular fracture, so it looks like we have a ductile brittle transition, but the toughness is still 100 megapascal root meters. So that may look brittle, but it certainly isn't. And so this material doesn't even have a ductile brittle transition, and it's body-centered cubic. Fascinating, really interesting material. And you can see the toughnesses are highest probably at room temperature, but they're still extraordinarily high for a BCC material at liquid helium temperatures. So the mechanisms are a little bit different. We get formation of an omega phase down at this very low temperature, 20 degrees Kelvin, and we get cracks that are jumping over boundaries. There's a little bit of bridging here, which is like a ceramic mechanism, but this is associated, we think, with where the cracks forming the boundaries is where the phase transformation to the omega phase forms. So it's a very, very interesting material. We have a paper which is in review now to try and understand this, but it's quite different to anything we've seen before. So what is the ductility of these materials? Well, that's a key, of course. They all have strength with these multiple principal elements, but the ductility is what gives them the toughness combined with the strength. In the FCC, I've explained it's a production, a sequence of mechanisms by deformation, slip, stacking faults, twinning, and then the formation of a phase transformation gives you prolonged strained hardening, and that gives you high toughness. And we think these alloys are probably the toughest ever been formed. The BCC materials have also a sequence of different mechanisms, but it's got nothing to do with strain hardening. We think it's associated with elements which give us promote more than one phase transformation. And this particular situation that we have, we call it NTTH with the niobium, tantalum, with titanium and hafnium, which are group 4, does a few things that are very interesting to generate these multiple slip forms which lead to the kink band formation. Just let me end with this. These alloys, there's a number of things going on here, I haven't explained them all, but these alloys have asymmetric dislocation cores, which tend to promote more than one slip mechanism. And so we think that's an important thing. The group 4 elements lower the unstable stacking fault energy. That's a toughening mechanism too. And we've done what's simple fracture initiation models with atomistic simulations. This is the Rice-Thompson mechanism for ductility. If a crack propagates by breaking a bond, that is a brittle mechanism, and if a crack propagates by emitting a dislocation and blunting, that's a ductile mechanism. And we see exactly that in these two alloys. In that very strong alloy I talked about that had terrible properties, that's the niobium, tantalum, molybdenum, tungsten, you can see the crack. This is as we increase the stress intensity, the crack propagates by breaking an atom at the crack tip. That's a classic brittle mechanism. But in the NTTH one with the group 4 elements, we don't see that. We see emission of dislocations from the crack tip and massive blunting of the crack tip. And that's consistent with a ductile alloy. So we think this approach, adding these group 4 elements, will give us the ductility we lack in some of the other alloys. These are nominally single-phase materials. They're not quite strong enough, so we're going to have to add precipitates to get the strength. It will cut back the toughness somewhat, but this is a very different body-centered cubic refractory high-entropy alloy. And one thing, just for the hell of it, we've done R curves based on those atomistic simulations. And this is probably the first time you've ever seen an R curve which is toughness versus crack extension. I've showed a lot today, but this is over right at the crack tip. So it's basically the first motions when the crack starts to propagate. It's done in terms of the crack tip opening displacement, which is a more easy model to measure. And of course, the ductile one shows a very, very steep R curve because the material is quite ductile, but the niobium, moly, tantalum, tungsten material shows brittleness because there's just the emission of a dislocation. So these are interesting differences in the BCC materials. So let me conclude by saying we've looked at these high entropy alloys. They're expensive, they're difficult to process, admittedly, but they have properties which are both unusual and very impressive. The BCC materials show these very high toughnesses, particularly at cryogenic temperatures, particularly at high strain rates, because of this sequence of deformation mechanisms. And we think these materials are probably the toughest on record. We've not seen any tougher. This is an Ashby plot, toughness versus high strength. And these are these alloys here. They're way at the top. The BCC materials are the ones that have much higher temperature properties. They have high strength, provided you're measuring compression, and they go to much higher temperatures than the alloys we currently have. But if we look at them on a toughness plot, we're way down here. We have high strength, but we have very, very low toughness. This is associated with, we think, with particularly grain boundary embrittlement and oxidation, and the lack of mechanisms to form dislocations. The ductile brittle transition temperatures are too high. But by adding group 4 elements, and the alloy we've been looking at is the niobium, titanium, niobium, titanium, tantalum, niobium, titanium, tantalum, hafnium, we can get these additional deformation mechanisms, these difficult slip modes, and we can generate other mechanisms of plastic deformation, particularly kink band formation. And we think these alloys may be the savior of what's been going on with the high entropy BCC materials, because potentially they have ductility. We've got to raise the strength. And that still needs to be done. Thank you very much for your attention.
Thank you so much, Professor Ritchie. Can I invite you to sit down in one of these chairs? We are having to, so we can have a debate.
No, I can stand, don't worry.
Yeah. And then, bom, obrigado a todos. Nós vamos ter debate e a plateia pode fazer as perguntas por escrito. Eu vou convidar, então, o professor Mark Myers, que é o editor-chefe da revista JMRT e é professor da Universidade da Califórnia, para participar do debate aqui. É claro que o debate não é restrito a nós, pelo amor de Deus, não é só para a gente dar um kick-off. E vou convidar também o professor Fernando Riso, professor emérito da PUC, para participar aqui como debatedor. E, por favor, vocês vão pensando aí, quem já pensou. Ali dizia para fazer. Tá? E aí vocês formulem as perguntas, se puderem, por escrito. A gente traduz, se for o caso. Se quiser falar, a gente chama vocês, tá? Mas vão pensando aí, porque é bem desafiador o assunto, né? Muito obrigado. Microfone para os debatedores, tem? Bem, eu vou fazer a primeira pergunta. Fui convidado pelo professor Maes a fazer a primeira pergunta. Eu vou fazer em português. Professor Ritchie, nós temos visto algumas tentativas de colocar mais elementos de liga nessas ligas multiprincipais, especialmente elementos que são face-center cubic. E quando você coloca esses elementos, em algumas vezes a gente tem detectado immiscibilidades. Por exemplo, prata, silver, apresenta immiscibilidade com os FCCs, com o Face Center Cubic, e cobre apresenta miscibilidade. Eu queria saber se o senhor tem explorado essa possibilidade, embora a gente já tenha tantas variáveis de composição na liga de Cantor, né? Se o senhor tem explorado essas possibilidades, você tem alguma ideia de por que adicionar um cubic, um elemento que já é cúbico de face centrada poderia causar immiscibilidade?
Yeah, that's a very good question. There are millions of alloys that are potentially out there now, and I think some of the computational studies are going to be useful to limit the number of sizes. There are probably 1 million alloys we could look at. We've looked at systems where we know the properties are quite well known. But there are many, many others that could be looked at, right? In the face-centered cubic materials, we are basically glorifying stainless steels, quite honestly. We're putting more into it. And we can get better properties, but there are other alloys. Mark has done quite a lot of work of been putting other elements in, but it's awfully difficult to do better than some of the initial alloys. That's the point. But this is why this topic has sort of revolutionized metallurgy, because the future is unlimited, right? There are billions of alloys we could look at. So I think you ask about silver. There's a lot of elements like that which people haven't looked at. But it's certainly worth looking at, and I think numerical approaches or atomistic simulations are a good place to start. But you can't predict microstructure with them. So that's the issue. But you can cut out the really brittle materials. But there's so much more to do in these alloys, is the point.
Thank you. Yeah. What really, I think, is Mark Asta doing the calculations with you?
In my program, I'm the mechanical type. Mark Asta does all the atomistic simulations. We share students, though. It's been very good. And then we have Andy Miner that does the TEM work. Mm-hmm. And we try to get all the students to do a bit of everything. So, but I've never been a big fan of atomistic simulation, but this has changed my mind, really, because it is a useful first start. It's not always reality, but it tells you something to get started, you know.
Okay, can I ask you the second question? I've noticed that you saw the BCC to be brittle in many cases, not tough enough, but you never seen cleavage, did you?
Haven't seen what?
Cleavage?
We don't see any signs of cleavage. Now, it's probably there somewhere in one of these alloys. But many of the alloys that contain the niobium, the group 4 elements, it's all ductile, normally ductile fracture. In the other alloys, the boundaries are so dangerous because of oxidation and other things there that they're always intergranular. We do see a bit of cleavage in some of these alloys at intermediate temperatures, but as soon as you get to high temperatures, it's all intergranular.
Yeah, that's kind of intriguing because...
Well, I didn't mention it, we did see a bit of cleavage at around 700 degrees centigrade, something like that.
Thank you. So I'll ask...
Professor Rizzo, you come next.
Okay, no, thank you. First of all, let me thank the organizers to invite me. It's an honor for me to be here in this conference and to be a part of this prize for Dr. Rich, which I know by name for a long time. And I think my question will just come into a more physical aspect. First of all, it's very interesting that the material has very good properties, both at very high temperature and a very low temperature. You have these very specific ways. What I'd like to know is this. We know that some base of these high entropy alloys is the sluggish diffusion and the distorted, structure. Do you think that these two components, at least, could be the reason why you can get that amount of different mechanisms when you explain, like going from sleep system to even like a trip? You go through all this spectrum of mechanisms, making the material more and more higher strength. Would somehow this being helped by these two components, I mean the sluggish diffusion and the distorted cell?
That's a very good question. One of the theories of this was called the cocktail effect, which is silly, really, but it says if you mix gin and tonic, you get a cocktail and it's tastier, right? Yeah. But I think what it is you've got multiple elements in there, and each of those elements is a dial. Yeah. And you can then dial, put some element in to promote one mechanism, another element to promote another mechanism, and that's why you can get these sequences. I think we were just lucky initially that they were all in, that all the stars were aligned. But future alloys, I think you can do that. And in these materials, I think dropping into the group 4, NASA did a lot of work on these alloys back in the 50s. So there's a lot of potential for getting very, very high strength, but also solving that ductility problem. And the ductility problem is just getting enough slip systems, and I think that's where the atomistic compositions can help. But it's like dials. You have a few things to twist. But I don't think we understand it all yet. There's no question about it.
Okay, very good. The other question which I'd like to ask is this. When you see that the high thermal stability, that you can work at very high temperatures, always bring the idea about how the materials behave in regard to oxidation. You have chromium, you have aluminum, which usually are beneficial for this. Could you comment on this? Like if this is already something that has been employed in practical use?
Well, that's the million-dollar question. I mean, these BCC materials just are not renowned for their, oxidation resistance, and so that's going to be an issue. But all the alloys we do use today at these temperatures, we put coatings on, right? And so I think that will happen. But every time we look at these alloys, we go to higher temperatures, we get something horrible happening, oxidation in the boundaries, something like that. So that is an area that needs to be studied in great detail.
And with regard to corrosion, like just
it's corrosion, oxidation, what it is, yeah.
Very good.
And the other one is fatigue. There's very little fatigue work here. Okay. And generally most alloys fail by fatigue anyway. So there's a lot of areas to look at in the future, I think.
Very good. Thank you.
I will just say one word directed to the audience. Who is studying high entropy alloys in Brazil? But there are questions from the audience.
Just trying to get the name of the person. He's congratulating on the very nice work on deformation mechanisms. And of course, since you are a fractured person, but then he's asking whether there's any studies going around or if you know and can give information about fatigue resistance.
Yeah, well, we've done a little bit of fatigue on the FCC materials. We're starting to look at the BCC materials now. And we fear that the kink band formation, which is good for toughness, may make fatigue more difficult. So there are lots of things to study. If you can make the materials, that's the difficult thing. If you can process them, that's even more difficult, but it can be done, of course. It's a really lovely area to get in because there's so many things that need to be understood, and the mechanisms are not quite the same as traditional alloys. These are not dilute solid solutions, they're concentrated solid solutions, and so things are a little bit different. So I think it's a fantastic topic for somebody who's young and wants to do something exciting.
Thank you. René, ficou claro? Ficou claro, hein? Professor Sérgio, está na plateia.
Sérgio Monteiro, do Instituto Militar de Engenharia. Excellent presentation. I really enjoyed very much. Indeed, in the past, I was, had a chance to see some of the presentations on more or less the same type of high entropy alloys, improvements.
Yep.
And now I'm really surprised. I'm really amazed how you came to that. My question is, may I ask you a question in Portuguese so everyone will be able to,
Yep.
okay? Could I ask a question in Portuguese?
Yes.
Please. Yes? Ok. Eu estou pedindo para o professor Rich, né, vai responder a pergunta. Eu vou fazer essa pergunta em português, talvez seja mais fácil de vocês, né, entenderem. Ele apresentou um gráfico ali que chama-se de Ashby. E o que tem de interesse nesse gráfico? Ele mostra praticamente todos os materiais que a gente estuda até hoje, mostra a tenacidade à fratura, a capacidade dele resistir impacto e a resistência desses materiais, quanto eles podem resistir ao máximo ali. O que tem de interessante nesse gráfico? Os maiores materiais que a gente consegue, tanto num caso quanto no outro, são exatamente as ligas de alta entropia que ele está estudando, que ele comentou agora. Isso é absolutamente fantástico. A pergunta que eu faria, Robert, você mostrou, inclusive, indicou que alguns desses trabalhos que você vem sendo realizados estão, inclusive, em revisão, não é? Ainda estão praticamente sendo julgados pelos revisores e eu imagino que a sua ideia seja ampliar esses limites desses materiais, tanto os cúbicos de face centrada quanto os cúbicos de corpo centrado que estão ali embaixo, não é? Mais resistência, mais tenacidade à fratura, tanto em um quanto no outro caso. Quais são as suas ideias para que isso possa ser ampliado? São novos elementos que você pretende introduzir, new elements that you intend to introduce, ou, certo, novos mecanismos que possam aparecer, como, por exemplo, kink bands, aqueles twinning, as máquinas que você mostrou que foram fundamentais para ganhar toda essa situação de materiais cada vez mais resistentes, cada vez mais também tenazes.
Well, that's a really difficult question, of course, but I think one of the things about Ashby plots is we're interested in open spaces, which is to move, as you said, to move these bubbles in different directions. I think with respect to toughness, we've probably reached the limit. I don't think we're going to go much higher in toughness. I really don't. But I think that in terms of strength, and I don't think we need that much more toughness, quite frankly. But in the BCC materials, we have to generate strength in the ductile versions. And the only way to do that, I think, is to add precipitates. And we need to add precipitates which somehow don't oxidize or coarsen. Yeah, second phase. I mean, most of this is single phase at this stage because we can see the mechanisms. But I think that's the next stage. And if you look back to the early days of NASA, they were doing a lot of work with niobium tungsten alloys where they would put precipitates in. But we better understand that now. We can put coatings around the precipitates. So there's all sorts of issues. So I think my feeling is the biggest potential will be to take these group 4, group 5 elements that we talked about in those alloys and then put precipitates in to drive the strength up. You won't you'll lose a bit of toughness, but you have plenty of toughness there to begin with. Then you'll have a really big refractory alloy that can operate at high temperatures, not fall apart in tension. I think the big driver for this is space acceleration, because for space acceleration, you want alloys to be able to tolerate large variations in temperature, right? Very low temperature, very high temperature. That's a problem with a lot of alloys. These alloys, and there's others we've looked at, have that potential. But I think for regular, very high temperature properties in rockets and hypersonics, it's putting a second phase in I think those group 4, group 5 element alloys is going to have the biggest impact.
Okay, you have a question from the audience. We know that superalloys are currently, a lot of them are just limited by melting temperature for aerospace application. The question is interesting, is whether you think it's possible to gain some knowledge that can be transferred to other superalloy properties, especially mechanical behavior of superalloys from what you're doing. Not from melting point, because that's a given, but you think some of what you're seeing on these alloys would be transferable, or would give ideas or insights of what could be done in superalloys?
Well, I honestly don't know the answer to that question. I think it's a little bit doubtful. But again, just these alloys are not easy to make because they require often very high temperatures. The problem with them is that after you've formed an ingot, you've got to break down the cast structure. And a lot of the refractory elements in them mean that you have to do that at just ridiculously high temperatures, which can't be done in many places, or very expensive. We can do it at room temperature in our group 4, group 5 element. But I think additive manufacturing techniques can solve that problem. And I think, to answer your question, that's where it can be usefully done. You can start to trim the elements much, much easier fashion than using traditional processing. So I think, I don't know the answer. I don't think it's going to work, but it's certainly worth looking at,
Okay, I have a question on additive manufacturing.
Yeah.
Are you doing that regularly? Because, I was very impressed with some work that we've done with stainless steel. And it was beautiful, and also with nickel-based superalloys. It was beautiful to still see segregation in the solidification of this laser. Although the size scale is ridiculously small compared to a weld or to a casting. So do you see any segregation in your alloys when you do this?
There's a million problems there, right? We get it done in Singapore because they have masses of 3D printers, but it is a potentially difficult issue. I think in the future it'll dominate a lot of what we do, because you can do things you can't do any other way. But there's so many things that can go wrong. You form porosity, you form voids. It's expensive. So I'm wondering about that. But I think the issues, from a research point of view, it enables you to make alloys you couldn't make any other way. I like it because I'm also do natural materials. And of course, natural materials are built from the bottom up. And that's how you do 3D printing, right? Conventional processing, you have a big blob and you go top down. So I think there's a lot of potential there. But I think all sorts of things, once you get into making components for aerospace, for example, with 3D printing, how do you do the non-destructive testing? Because you're looking at tiny little defects and so forth, or lots of them maybe. So there's all sorts of uncertainties there. But I think 3D printing is a way to solve a lot of the big problems that we've had to face.
Mais perguntas? Joaquim? I'm still intrigued with the BCT. Let me ask you a question. If you were able to remove those oxidations, if you did everything under a very protective atmosphere, do you think there would be any toughness? Because the bad alloy, the bad BCT, to show us failing mostly by environmental issues. Of course, environment is everything, I agree, but if you do it intrinsically, you think they could have better properties?
Yeah, I think so. I mean, this alloy wouldn't. I mean, I think at the temperatures of 1200, it's starting to recrystallize. Shitang has looked at a similar material in China, and he finds that he gets superplasticity up there. But we don't have a vacuum system. We just pump in argon, and that's not enough. But I think they probably are pretty good in some of these alloys are pretty good under conditions of non-environmental. But if they have a very poor compressive strength, they're not going to be very good. So I think these Group 4, Group 5s are the way to go. They have the ductility. They don't have the strength. You can solve the strength by some second phase. Then potentially they may have, and then you have to solve the environmental effects. But I think that can be done. The environmental effects are always the last thing anybody studies, and they're the worst thing to deal with, I'd say. Just fatigue. But I think they have tremendous application. But people think they're going to replace super alloys. They might, but it's not going to happen for a while.
You just mentioned when we were showing there one of the graphs, it was very interesting that you have like a very constant level of stress and just like superplasticity, like you mentioned. What would that be, the motion, like the twin?
Twinning is a very dominant mechanism in this material. It's intriguing though, because you have high toughness and there's no strain hardening that you see with the FCC. So it's a different mechanism. But I think a lot of these mechanisms just provide plasticity for material. And the kink bands should be softening. They should promote instability, but they move the deformation away from the crack tip. And the twinning, and a lot of the order of the mechanisms is changed, by the way. The formation of the phase transformation to promote the twinning rather than the other way around. So there's all sorts of peculiar things going on. I didn't talk much about that, but that's what we're trying to study now. So, but it's very, very different. There's no strain hardening. You can see it's just a sequence of mechanisms again.
Yeah, and I understand that when you do the correspondence, like use the trip effect, would be something like from FCC to HCP. And moving like you have some like just as like accommodation of the phase shifting from one to the other.
Yeah.
It's like the problem.
Yeah. I mean, the omega is not good, just like the phase transformation in the FCC materials. The formation transformation has a benefit, but you don't want too much of the product phase. That's
very well. Yeah, very interesting.
Professor Ricci, thank you very much for your words. I'm Wilker, and we representing it's a university here in Brazil. And my question is, I wish I had more knowledge to enjoy the knowledge you use, sir, on this subject, but I'm only on my second year of university, so that's tough for me. But one thing that I'm trying to understand is why it is so important for the industry to study this kind of high entropy alloys about strength and ductility. What I want to mean, why do we have to manufacture something that have this relation about strength and ductility in the industry? Thank you very much.
That's a very good question. It's a question I never answer. I'm funded by department. Yeah, I'm funded by the Department of Material Science Engineering in DOE, and we're not even allowed to talk about applications in that. But I think it's a good point. These alloys are expensive. They're not going to replace steels to make rebar or ships and bridges, that kind of thing. But for extreme applications, very, very high temperatures, contact surfaces on hypersonic vehicles and what have you, they potentially have higher strength properties at much higher temperatures. A lot of things have to be solved, but it's like intermetallics were in the 80s and 90s. They had different properties, but they had detriments. So Industries sort of, I think, should sit back from that. Just let research see what's going on. But if you're into something like space, for example, there was a class of alloys called bulk metallic glasses, which were amorphous. They've never had much application, but NASA is now making lots of objects for space, vehicles on planets and stuff, because these alloys have an extreme range of temperatures. They're expensive, and that's where the applications could. These materials could certainly be used for those situations. Money's no object in those situations, right? But remember, when it comes to structural materials, and you make a new structural materials, the first thing people ask you is, what are you going to do with them? This is not asking about a new chip for an Apple phone, where it would happen in the next 6 to 10 months. In structural materials, it takes decades before they actually put in. I mean, ceramic composites, for example, are now used in a limited way in gas turbine engines. They were invented 30 years ago. Regular composites are used in airframes, the Boeing 787, but they were invented in the 60s. And so it takes a long time to happen. So when these polymer composites were first developed, if someone had asked the developer, what are you going to make with them? What are you going to do with them? The correct answer would be to make better tennis rackets, to change the game of tennis, to make better skis or something. And that's where they have the applications. So it's kind of difficult. It's a very good question to ask, but it's a very difficult question to answer. So, because it takes a long time. It's a good job it takes a long time as well. But I think these are expensive alloys, that's the problem. And they're expensive to make. So the applications will have to be fairly specific. But for me, that's somebody else's problem. It's my problem. It's a very interesting area of research to me. Okay?
Thank you so much. Yeah. Alguma pergunta mais, pessoal? So, Professor Richard, I'd like to thank you very much for this opportunity. Thank Professor Myers, Professor who's our co-worker. Yeah. And thank you, Professor Rizzo. E lembrar vocês todos, por favor, que nós temos eventos logo depois do almoço. Agora vai ter uma pausa para o almoço. Né? Por favor, chegar o mais próximo possível do horário. Né? Eu vou fazer só um comentário. Hoje, as nossas turbinas, se você pensar, desde o Boeing 707, que vocês não devem ter nem ouvido falar, né? Foi o primeiro avião que eu viajei para a Europa. Ele voava a 800 km por hora. Hoje, o 787 voa a 800 km por hora. Tá? Porque ele tem uma barreira aerodinâmica e tem uma barreira de propulsão. Então, os Estados Unidos tem, desde a década de 90, como ele falou, um projeto de aviões hipersônicos. Então, um avião capaz de chegar na Europa em 2 horas. Tá? E, para isso, você não vai poder trabalhar com as superligas que ele trabalha, porque elas fundem a 1.300, 1.400 graus. A turbina tem que operar, para ter uma eficiência termodinâmica suficiente, tem que operar 1.600, 1.700, aquelas temperaturas que ele mostrou ali. Então, a gente está, todos nós loucos, procurando material para fazer as paletinhas da turbina, que não derretam. A gente já está a 10 graus de temperatura de distância do líquido. Quando você estiver viajando no avião, pense nisso. A sua turbina está a 10 graus de fundido. Sério, não é brincadeira, o voo inteiro ela está a 10 graus de fundido. E não funde, graças a Deus. Tá? Então, é isso que ele falou. A gente está pensando em materiais que vão resolver os problemas para a gente dar um salto. Tá? Não é um salto evolutivo. Não. O que ele está falando aqui é realmente inovação. Não é um aço melhor, não é um aço triplo. É outro patamar. É você diminuir de 8 horas para 2 horas de viagem transcontinental. Tá? E, para isso, o governo americano tinha, espero que ainda tem, um interesse em investir. Tá? E, naturalmente, o que disso se desenvolva para fins militares é absolutamente importante, tá? Que é o campo de provas, onde você vai experimentar essas coisas. Ninguém vai fazer um avião comercial, botar a gente lá dentro antes de testar isso em turbina de avião de guerra. Tá? I'm just trying to... Okay, so
Não, eu só quero agradecer. I would like to thank eu gostaria de agradecer aos presentes aqui a assistirem à palestra do professor Ritt. Eu coloco um desafio para os estudantes brasileiros, para os jovens brasileiros que entrem nessa área e contribuam para ligas de autoentropia. Eu não estou ciente de quais grupos estão estudando, mas eu acho que é uma área muito fértil para a pesquisa e aqui seguindo os passos do professor Ritt e do grupo dele de Berto. Tá? Eu gostaria de agradecer muito ao professor Ritt essa palestra, ter vindo aqui ao Brasil, neste momento aqui, para ser homenageado pela nossa revista JMRT, que o escolheu como o maior cientista global deste ano. Muito obrigado.
Obrigado a todos pela presença.